Hey everybody, welcome back to another round of astronomy, and yeah, let's get going. Displayed for you here, I have an image of the Orion constellation, and you'll notice this is roughly what you could see if you could just collect light for about 200 hours. Okay? So it's not falsely colored. This is actually what you can see. It's just that our eyes aren't good at, collecting all of that light and adding it together. So this, of course, has been done digitally. Now, the thing that I want to point out to you here, and as I've asked you to go out and study in your star chart, is notice the difference in color between Betelgeuse and Regal, right? You see that? That is real. Okay? And that tells us some very interesting stuff about the temperature of those two stars. So we would like to, today's discussion will formalize that relationship. How can we use the color, maybe I should be more specific, the wavelengths of light emitted by these stars to associate them with surface temperature? Ready for it? Yeah, good. So I'll start off with this. Which stove burner would you prefer to touch? Yeah, you see. And from a very early age, we start to learn that the light emitted by some objects tell us that that object is hot, as versus the light emitted by other objects, that object is cool, it's safe to touch. Okay? The stove burner would be the prime example. Because of the light emitted, that we can infer something about the temperature. Okay? Now, before we get into the formal association between color and temperature, we should take a byline and discuss what temperature really is. How do we conceptualize temperature? Now, unfortunately, the majority of us, myself included, have grown up with a completely bogus temperature scale, okay? The Fahrenheit scale. Okay? Unfortunately, in science, we do not use Fahrenheit. Okay? We have this other scale, which is a little bit closer to what we use in science, called the Celsius scale. If you need to formalize, if you need a formal temperature, here's the actual conversions. Okay? So you can see the minus 32 in there. That's to get the relative starting point of the two scales roughly the same. And then the 5/9 basically tells you the conversion between Fahrenheit and Celsius. Okay? So in terms of temperature, 1 degree Celsius is a lot larger of a jump than 1 degree Fahrenheit. Okay? The advantage to the Celsius scale is that the numbers are a whole heck of a lot easier. Okay? Now, in science, we tend not to use the Celsius scale very much either. There is a third temperature scale, which is probably the most important, and I'll have to give you why we have this set up. It is called the Kelvin scale. Now, as you see in this figure down here, the Kelvin scale is a bit different. Okay? You'll notice that the boiling point of water is at 373, which seems to go against this idea of using nice round numbers. Okay? And the freezing point of water is 273. Again, that seems really weird. Okay, why would we do such a scale? And we see that at the bottom, this is the key. At the bottom, it's 0, okay? What we call absolute 0. So the advantage to the Kelvin scale is not that the numbers are easier. Okay? It's not that they're round like the Celsius scale. The advantage to the Kelvin scale is that all the numbers are positive. You cannot have a negative temperature on the Kelvin scale. You say, what? That seems, why? What's going on there? Let me try to give you a little bit of a sense of what temperature actually is. Okay? So here's a question for you. For a given material, pick your favorite material. Okay? Which phase of matter are the atoms moving the fastest? Yeah, you got it? Yeah, good. And if you remember from our science classes, probably in elementary or middle school, I don't remember which. Okay? If you remember, when we start learning about the phases of matter, you have the solid phase, where we think of atoms as connected by springs, and those atoms are locked into position. Sorry, let me draw those a little bit bigger. Those atoms are locked into position. In other words, they can jostle back and forth a little bit, okay? But they have to maintain their relative position. It's not like this atom can all of a sudden be on the other side, right? It is tied into place by those connecting springs. And because of that, you have objects that maintain their shape. It is really hard to deform them, right? You can maybe bend them a little bit, but they maintain their shape if left alone. Well, what happens if we heat that object up, right? If we take this solid object and we start heating it up, eventually what you end up doing is you break those connections. So now these atoms are no longer held together in a structure. They are free to move. They're free to slip past each other and move around and circulate as they see fit. Okay? The issue is they don't have a defined structure. Rather, they take the shape of whatever the container is. Now notice, however, that they are still touching each other. They're still forced to the bottom of the container. Okay? So this is what we would refer to as the liquid phase. Okay? Well, what happens if we keep heating that up? If I keep heating it up, eventually we can break some of these very weak attractions between the atoms, and now they're free to zip around the container, and not only do they fill the bottom of the container, but now they're allowed to be anywhere. Okay? And of course, this is what we would call the gas phase. So I'm banking on this idea. For a given material, the gaseous phase is the one where the atoms are moving around the most, the fastest. Next question, corollary question. For which phase is the material at the highest temperature? Yeah, good. Again, the gaseous phase. Okay. So, in the gaseous phase, first of all, the atoms are moving the fastest. Therefore, they have, per atom, the highest kinetic energy. And we call that, we also know it has the highest temperature. And so we have an idea here that allows us to transition from a macroscopic observable to infer a microscopic quantity. That is what temperature really is. Temperature is a way for us to make a macroscopic observation and infer something about how quickly the microscopic atoms are moving. So returning to the Kelvin scale, this is exactly why the Kelvin scale exists. At lower temperatures, we can say that the atoms of an object have less kinetic energy. Okay? Well, next question. What's the lowest amount of kinetic energy that an object can have? Survey says 0. Good, right? You cannot have negative kinetic energy. You can have no kinetic energy, but you can't have negative kinetic energy. That sounds a little bit familiar. So absolute 0, the reason why the Kelvin scale has been set up as it has been is because it sets the lowest possible temperature, and I mean a physical boundary, at 0. Okay? And that is the temperature at which all motion, all microscopic motion of an object stops. Okay, good so far? If you would like the temperature in Kelvin, you simply take your temperature in Celsius and add 273. Technically, it's something like 273.15, and there's some extra digits here. I don't care about that. We'll just say 273 and call it a day. Okay? Good. So let's keep going. So that takes care of the temperature bit. We need to come back and take care of the color bit. Right? So that brings us to our second idea. Okay? I need to give you an idea about what a spectrum is. And no, I don't mean the rebranded Time Warner spectrum. Okay? What I mean is the spectrum of light. When we discuss light, a spectrum is very helpful. What you are doing is you are taking light and you are spreading it out into its various wavelengths. Okay? Nature naturally does this for us, for example, as displayed here over one of Graham's soccer matches. Yeah, where does a rainbow come from? Where is the light for the rainbow coming from? Yeah, the sun. Not shown in this picture. I'm facing one way. The sun is behind me. And what is happening? Sunlight is being passed through and being divided up into its individual wavelengths. Well, from the visible part of that spectrum, we see that the different colors end up being separated. What's doing that separation? Yeah, water drops in the air. Now, there's a couple ways in this class that you will see spectra presented. The first one, I will call it, for lack of a better term, I'll call it kind of the visual spectrum. Okay? So here for you, what I have is a wide range of wavelengths. Okay? And again, this only works in the visible part of the spectrum. I can't do this kind of representation for X-rays or for gamma rays because our eyes don't pick up those quote-unquote colors. Okay? Now, what you see here is generally referred to as an absorption spectrum. You notice that you have all of the wavelengths present, except for very specific wavelengths, which have been removed or are absent from the spectrum. You have a rainbow background and certain wavelengths or colors have been removed. Now, of course, what do we do if that spectrum extends beyond visible light? Okay. And that's where I'll give you the second representation. I call this more like a graphical representation. Okay. So let me walk you through. On the horizontal axis, we have the wavelength. And now, instead of saying color, I truly mean wavelength because you can extend this graphical representation beyond the visible spectrum. On the vertical axis, we have intensity, how bright each wavelength is represented. Okay. So you notice, and it's not by accident, you notice that where there is an absorbed wavelength, that corresponds in the graphical representation with a dip, a drop in intensity. So these two are trying to convey the same information. Personally, the visual representation is nice if we're doing something, for example, in lab. You are going to use your eyes to see spectra, and then you're going to need to draw it out. So this visual representation will be good for that. But if you want to quantify, if you want to use actual numbers, our eyes are terrible for gauging numbers, right? The graphical representation will be better when we try to quantify how bright is a particular wavelength. Now, I've called this an absorption spectrum, but you also have what is referred to as an emission spectrum. And it's exactly, if you will, the negative or the inverted kind of scheme from what you see here. What I mean by that is that rather than having a full wavelengths, or all the wavelengths, and then removing a specific set, you have kind of the opposite of that. You have no wavelengths present except for very specific colors, wavelengths. And graphically, go ahead, think about what would the graphical representation of the spectrum look like. You got it? I mean, pause the video, draw it out real fast. What do you think it's going to look like? Okay, good. You have low intensity, almost no light present for a little bit, and then you should see a blip for the purple light. And then you should see nothing, and then a blip for this next purple line, etc., etc. So the graphical representation would look something like this, where you have only small jumps where those lines are present. Okay? So that's the second piece, is this idea of spectrum, dividing the light up into its constituent wavelengths. Okay? Last piece of information I give you, and then we'll pull all of this together to relate temperature to an object's spectrum. Okay, that's the thing that I wanted to use. We will look at the spectrum of an object in order to infer its temperature. Now we have to do this with a very, very special type of object. Okay? And so that's the last thing I need to give you, is that these objects, in order to make this relationship, we have to deal with objects which are referred to as blackbodies. A blackbody object is an object that does not reflect light. Okay? Hence the word idea black. Okay? Black, that color black, absorbs any light that falls on it. Okay? The reason why a black cloth looks black is because all of the wavelengths of light that strike it are absorbed. Now, the second piece I have to be careful about is the object does not reflect light, but it can emit light. So it cannot reflect light, but it can emit light. What that means is any light that falls on the object is absorbed, okay? And then it emits its own spectrum. Okay? So it can emit light. And the spectrum of such an object, okay, we call it a black body, the spectrum of a black body always resembles the same shape. Okay? What you get is that for short wavelengths, high frequency, you're going to get a gap. There's not going to be very much light being emitted. Then you have a rapid rise to the peak. Okay. And then you have this long, drawn-out tail. You'll notice that it's asymmetric. And this tail of a black body spectrum, that tail will continue on. Here, let me get a different color so you can see it against the black. That tail will continue on and on and on and on, and eventually it'll go back to zero. So what I've got for you here, click on the link, fly out, boom. What we've got is a little simulation that allows you to look at the black body spectrum and see how it changes as you adjust the temperature. And you'll notice that as the temperature changes, you can get it kind of more spread out or less spread out, but that general shape still holds. The other thing that I'll point out is that you'll see, let me add a curve here so we can do a comparison. You'll see that as the temperature goes down, the peak tends to be smaller. Okay? And as the temperature goes up, as the temperature is larger, you'll notice that the peak grows. Okay? And I encourage you, go ahead, play around with this black body spectrum simulator. You can kind of see what the various spectra will look like, how it changes with temperature. Okay? Now, we will quantify that. Okay? Wien, a physicist, scientist, noticed this relationship, noticed this pattern about the shape of a blackbody curve, spectrum, and the temperature of the blackbody. And he was able, and we won't go into the little nitty-gritty details, he was able to discern a pattern. His pattern is what is today known as Wien's law. The pattern was this. Okay? If I look at the peak wavelength, I've put it as lambda max. Sometimes you will see it as lambda peak. There is a relationship between the peak wavelength and the temperature of the object, and I'll put in here, this is in Kelvin. And specifically, it is an inverse relationship. Okay. Now, what is lambda max, or the peak wavelength? I do not mean the longest wavelength in the spectrum. Rather, what I mean is it is the location of highest intensity. Okay. The location of highest intensity. So what this requires you to do is look at, first of all, you have to obtain the spectrum. Okay. Then, using the spectrum, you identify the brightest, the most intense wavelength, okay, what I refer to as lambda peak. Once you identify that peak wavelength, you can use Wien's law to infer the temperature of the object. Good? Awesome. I'll finish off with this. Remember when I started off with the introduction about light, I gave you a little video snapshot of the Crab Nebula. And I said, hey, if we look in the visible regime of light, we cannot see the central star in this nebula. Rather, we have to go to X-rays or even gamma rays in order to really discern the star. Well, why is that? Yeah, you've got the answer now. It's because that star is so hot. Because that star is so stinking hot, the peak wavelength of its blackbody spectrum is really, really tiny in the X-ray regime. So in order to really discern that central star, we have to go to X-rays in order to see it. Okay, let's get an idea. Go ahead, apply Wien's law. Here is the spectrum of the sun, and the green is the ideal blackbody curve. So in this class, we'll go ahead and assume that every object can be treated as a blackbody. And even though the sun is not a perfect blackbody, good enough for our use. Go ahead, apply Wien's law, give me an answer for the approximate value of lambda max. You got it? Yeah, good, good, good. And of course, I'm asking you to read from a graph, so we're all gonna have slightly different values. So I'll walk you through, but the first thing is, again, realize lambda max is not the maximum wavelength. So if you put something like 1800 or 2000, I say, oh, nay, don't do that, okay? That is not lambda max. Lambda max is the location of the peak. So for me, I'll say something, it's between 400 and 600. It's roughly around 500. Okay. Oh, incidentally, 500 nanometers. Remember, 400 nanometers corresponds to what color of visible light? Yeah, good, blue. So you got blue down here. How about 700 nanometers? This corresponds to, yeah, red. Okay. So if you remember Roy G. Biv, the order of the colors, 500 is going to be somewhere around the yellow-green portion of Roy G. Biv. Okay. Next question for you. Now that you have an idea about the max wavelength, give me the surface temperature of the sun. You got it? Good, 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 good. So I've put down Wien's law here, okay? And probably the one other piece that we need to remember, lambda max has to be in meters. We're working in the international system of units. Temperature has to be in Kelvin. So first of all, I'm going to get temperature by itself. And now here's the thing that we have to be careful about. If you plugged 500 in, you're on the right track, okay? Or some comparable number. The piece that we have to remember is look at the units of the horizontal axis, right? Yeah, what are those units? NM. It's a prefix, by the way. M is the standard unit of distance. Meters. Good. What's the prefix N represent? Yeah, good. This is nanometers. Meters. So we have to remember nanometers. What's nano? That is given by 10 to the negative ninth. When you see nano, that corresponds to 10 to the negative ninth. So this is 10 to the negative ninth meters. So if I want to apply Wien's law, I don't put 500. I have to put 500 times 10 to the negative ninth. There's the nano. And so we go ahead. Yeah, there we go. Cool. Now we have the surface temperature of the sun. Yeah, good. Okay, I think I'll leave it there for right now. But keep up the good work. Keep thinking about Wien's law. And of course, if you need some extra practice problems, just let me know and we'll try to get something together. So hey, I thank you for your attention. Keep up the good work. I'll see you next time.